There is a star in the southern sky that could explode at any moment, not in 1,000,000 years, not in 100,000 years. It could happen tonight. It could have already happened, and the light simply has not reached us yet. This star is not Betelgeuse. It is not the famous red shoulder of Orion that has dominated headlines and social media feeds for the past several years. This star sits lower in the sky, buried in the curving body of a scorpion, glowing with a deep and ancient red that early civilizations found so unsettling they named it the rival of a god. Its name is Antares, Alpha Scorpii, the heart of the scorpion, and it is one of the most massive, most luminous, and most dangerously evolved stars visible to the naked eye. Yet almost no one talks about it. When most people think of a star that is about to explode, they think of Betelgeuse. It has become the celebrity of stellar death, the poster child for what astronomers call a supernova candidate. Entire documentaries have been built around its dimming episodes. News outlets run breathless headlines every time its brightness fluctuates. And yet, sitting in the opposite part of the sky, visible from late spring through autumn for much of the world, there is another red supergiant that has been dying just as spectacularly, just as inevitably, and in some ways more mysteriously, with far less attention from the public eye. Antares has been overlooked, not because it is less impressive, but because it has been less theatrical. It has not produced the kind of sudden, dramatic dimming that generates headlines and viral posts. It has simply continued to burn, red and immense and patient, while its interior races through the final stages of nuclear evolution at a pace that defies our ability to track it. Almost no one mentions Antares in the same breath as its northern counterpart, the reddish star Betelgeuse, which has captured the imagination of millions. Antares sits in a quieter region of the sky, rises lower above the horizon for observers in the northern hemisphere, and has not produced the kind of dramatic dimming event that thrust Betelgeuse into global headlines. But make no mistake, Antares is every bit as massive, every bit as evolved, and every bit as close to the end of its life as Betelgeuse. Some evidence suggests it may be further along. When Betelgeuse dimmed in late 2019 and early 2020, the world briefly panicked. Headlines screamed about a possible supernova. Social media erupted with excitement and fear. Astronomers rushed to explain that Betelgeuse was likely just shedding dust, not dying. And they were right. The dimming was caused by a massive surface eruption, not an imminent explosion. But during that entire frenzy, almost nobody mentioned that there is another red supergiant, one that is arguably larger, arguably more massive, and sitting at a distance that makes its eventual death a spectacle unlike anything humanity has ever witnessed. Antares has been quietly aging in the constellation Scorpius, burning through its remaining nuclear fuel at a staggering rate, swelling to a diameter so vast that if you placed it at the center of our solar system, its outer atmosphere would swallow the orbit of Mars and possibly reach toward Jupiter. It would fill the sky from every planet in the inner solar system. Mercury, Venus, Earth, Mars, all of them would be inside the star. The numbers are difficult to absorb. Antares is roughly 700 times the diameter of our Sun. It is perhaps 12,000 times more luminous. Its mass is estimated at somewhere between 11 and 14.3 times the mass of our Sun, though some models push that number even higher. It sits approximately 550 light-years from Earth, which in cosmic terms is uncomfortably close. Close enough that when it finally detonates, it will become the brightest object in the night sky after the moon. Close enough that it will be visible in broad daylight. Close enough that for weeks, perhaps months, it will cast shadows on the ground at night. Shadows from a star that, until that moment, appeared as nothing more than a modest red dot to the unaided eye. And unlike Betelgeuse, which has received enormous public attention, Antares has been studied with a level of quiet intensity that suggests the scientific community knows something the general public does not. Not a secret exactly, more of an unspoken acknowledgement. Antares is not just a candidate for supernova, it is a leading candidate. It is a star that has already entered the final stages of its nuclear evolution, fusing heavier and heavier elements in its core, racing through a sequence of reactions that each last shorter than the last. The final stage, the fusion of silicon into iron, takes only about 1 day, one single day, and then the core collapses. Everything that happens after that unfolds in seconds. By the end of tonight, you're going to understand why Antares deserves as much attention as Betelgeuse, perhaps more. You are going to understand the physics of what is happening inside this dying giant, the timeline of its collapse, the consequences for everything within hundreds of light years, and the strange, almost philosophical weight of knowing that one of the brightest stars in our sky is a bomb with an unknown timer. You are going to understand why some astronomers consider Antares the other red supergiant death candidate, and why that phrase carries more weight than it might seem at first. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. To understand why Antares matters, we first need to understand what it is and what it is not. Antares is a red supergiant. That is a classification, a stage in the life of a very massive star, but the word supergiant barely begins to capture what we are dealing with. Our Sun is a main sequence star, a yellow dwarf, burning hydrogen in its core through a process called nuclear fusion. It has been doing this for roughly 4.6 billion years, and it will continue for another 5 billion or so. It is stable, it is predictable, it is, by stellar standards, ordinary. If you could line up all the stars in the Milky Way by how much attention they deserve from astronomers, our Sun would be somewhere in the unremarkable middle. It is a perfectly average star, living a perfectly average life. Antares is none of those things. It began its life as a hot, blue, extraordinarily massive star, perhaps 15 to 18 times the mass of the Sun, burning through its hydrogen fuel at a rate so ferocious that its total lifespan will be measured not in billions of years, but in millions. Massive stars live fast and die violently. This is one of the fundamental truths of stellar astrophysics. A star like our Sun will eventually swell into a red giant, shed its outer layers gently, and leave behind a white dwarf, a dense but quiet remnant roughly the size of Earth. A star like Antares will do something fundamentally different. It will loot, not gently, not quietly. It will detonate with more energy than the Sun will produce in its entire 10 billion year lifetime, compressed into a few seconds of absolute violence. But we are getting ahead of ourselves. Let us start with scale, because scale is where the human mind begins to lose its grip on what Antares actually is. If the Sun were the size of a standard doorway, roughly 2 meters tall, then the Earth would be a small marble about 18 millimeters across, sitting about 215 meters away. On this same scale, Jupiter would be a basketball roughly 20 centimeters in diameter, sitting over a kilometer away. The nearest star, Proxima Centauri, would be another doorway-sized object sitting approximately 550,000 kilometers away, which is roughly 1.5 times the distance from the Earth to the Moon. That is the distance to the nearest star. Space is vast in a way that resists intuition. The spaces between things are so much larger than the things themselves that it breaks every analogy we try to construct. Now place Antares on that same scale. If the Sun is a 2-meter doorway, Antares would be a sphere roughly 1.4 kilometers in diameter, 1,400 meters across. You could fit the entire Sun inside Antares approximately 343 million times by volume, though the exact number depends on which measurement of its radius you use. That number is worth pausing over: 343 million suns packed inside one star, and yet Antares contains only about 12 to 14 times the mass of the Sun. The rest of that enormous volume is occupied by gas so thin that it would count as a vacuum by any earthly standard. Antares is so large that it was one of the first stars ever to have its angular diameter measured directly. In 1920, Albert Michelson and Francis Pease used an interferometer mounted on the 100-inch Hooker telescope at Mount Wilson Observatory to measure the apparent size of Betelgeuse, and shortly after, similar techniques were applied to Antares. Even at a distance of 550 light-years, Antares is large enough that its disk can be resolved by modern instruments. Most stars, even through the most powerful telescopes, appear as points of light. They are so far away and so small relative to their distances that no amount of magnification can reveal their surfaces. Antares is different. Antares appears as a disk. That is how enormous it is. Let us try another comparison. one that brings the scale into sharper focus. If you could somehow drive a car around the equator of the Sun at highway speed, say 100 kilometers per hour, the trip would take roughly 182 days, about 6 months. A long road trip, but not an impossible one. To drive around the equator of Antares at the same speed would take approximately 349 years. You would not live to complete the journey. Your children would not complete it. Your grandchildren would not complete it. More than a dozen generations would pass. Empires would rise and fall. Languages would evolve and disappear before the car returned to its starting point. That is the circumference of one star. There is one more comparison that may help anchor the scale in the mind. Consider the relationship between a grain of sand and a football field. A single grain of sand is roughly 0.5 millimeter across. A football field, including the end zones, is about 109 meters long. The ratio between them is roughly 218,000 to 1. The ratio between the diameter of the Sun and the diameter of Antares is roughly 700 to 1, which is smaller than the grain of sand to football field ratio. But the critical difference is that we are not talking about lengths. We are talking about volumes. Volume scales as the cube of the diameter. So when the diameter increases by a factor of 700, the volume increases by a factor of 700 cubed, which is approximately 343 million. That is the number of suns you could fit inside Antares. 343 million. If each sun were a marble, those marbles would fill a building the size of a large sports arena, packed floor to ceiling. That is the interior volume of one star. One single, solitary, dying star in the constellation Scorpius. And here is yet another way to feel the scale. If you could somehow place Antares where our Sun currently sits, at the center of our solar system, its surface would extend past the orbit of Mercury, past the orbit of Venus, past the orbit of Earth, past the orbit of Mars. Some estimates suggest it would reach the asteroid belt between Mars and Jupiter, at roughly 3.4 astronomical units from the center. Every rocky planet in our solar system would be inside the star. They would not be orbiting it. They would be submerged in it, vaporized, dissolved into the stellar plasma like grains of salt dropped into a furnace. This is the object we are discussing. Not a star in the ordinary sense. A structure so vast that light itself takes over an hour to cross from one side to the other. When we look at Antares in the night sky, that reddish point of light, we are seeing a surface area thousands of times greater than our entire solar system's worth of planetary surfaces combined. We are seeing a dying furnace that pours out more energy in a single second than the Sun produces in several months. It radiates with a luminosity roughly 12,000 times that of the Sun, pouring energy into space with a profligacy that is difficult to fathom. And nearly all of that energy comes from the gravitational contraction of its envelope and the nuclear burning deep in its core, processes that are accelerating as the star ages. And yet, for all its immensity, Antares is surprisingly diffuse. Its average density is far less than the air you are breathing right now. If you could somehow scoop out a cubic meter of Antares from its outer layers, you would be holding a near vacuum, a wisp of gas so thin that it would make a laboratory vacuum pump seem dense by comparison. The mass is there, concentrated deep in the core, but the outer envelope has been inflated to extraordinary proportions by the radiation pressure from within. Antares is, in a very real sense, a thin shell of glowing gas wrapped around a small, incredibly dense and incredibly hot interior. Imagine a soap bubble the size of a city, with a marble at its center. The proportions are not too far off. This brings us to the constellation itself and the name that has echoed through human history. Antares sits at the heart of Scorpius, one of the oldest recognized constellations in human astronomy. The Sumerians recorded it more than 5,000 years ago. The ancient Egyptians associated it with the goddess Serket, protector against venomous creatures. The Babylonians called it Gira-Tab, the scorpion, and tracked its movements across the sky for agricultural and religious purposes. The Greeks saw it as the great scorpion sent by Gaia to slay the hunter Orion, and they placed the two constellations on opposite sides of the sky so they would never appear together. When Scorpius rises in the east, Orion sets in the west. When Orion dominates the winter sky, Scorpius hides below the horizon. Even in mythology, these two were kept apart, locked in an eternal separation decreed by the gods. The name Antares itself comes from the ancient Greek phrase anti-Ares, meaning rival of Ares or rival of Mars. The planet Mars, with its reddish hue, passes near Antares periodically as it moves along the ecliptic, and the ancients noticed that the star and the planet looked strikingly similar in colour and brightness. They named the star the rival of Mars, and the name stuck. It has endured for more than 2,000 years. In Arabic astronomical traditions, the star was known as Qalb al-Aqrab, the heart of the scorpion, a name that persists in some modern references, and that captures the anatomical precision with which the star was positioned within the constellation figure. But Antares is not alone, it has a companion. Antares b, a hot blue-white star of spectral type B2.5, orbits the red supergiant at a projected separation of roughly 550 astronomical units, which is about 550 times the distance from the Earth to the Sun. That is roughly 14 times the distance from the Sun to Pluto. Antares b is itself a fairly luminous star, perhaps 170 times as bright as the Sun, but it is utterly dwarfed by its companion. Observing Antares b is notoriously difficult, precisely because it sits so close, from our perspective, to an overwhelmingly brighter object. Astronomers have described its appearance as a small green or blue-green point, visible only when atmospheric conditions are perfect, and when the glare of Antares A is carefully blocked or filtered. The green appearance is likely a contrast effect, the eye perceiving the complementary colour of the dominant red light from Antares A. The companion matters for a reason that goes beyond curiosity. When Antares A explodes, Antares B will be caught in the blast. It will likely survive, supernova ejecta expand rapidly, but the companion is far enough away that it may not be physically destroyed, but it will be stripped of its outer atmosphere, blasted by radiation, and flung out of the system at high velocity. It will become a runaway star, hurtling through the galaxy at speeds of tens or even hundreds of kilometers per second, carrying with it the gravitational memory of a partnership that lasted millions of years. This is a detail that is rarely mentioned in popular accounts, but it adds a layer of complexity and, some would say, tragedy to the story. Antares does not die alone. It takes its companion's fate with it. The binary system that has existed for millions of years will be dissolved in a single moment. The fate of Antares B after the explosion is itself a subject of considerable astrophysical interest. When a supernova occurs in a binary system, the gravitational bond between the two stars is typically severed because the explosion ejects more than half the system's total mass in a matter of seconds. With the gravitational anchor suddenly removed, the companion star flies off in whatever direction its orbital velocity was carrying it at the moment of the explosion, like a ball released from a sling. The velocity of the ejected companion depends on its orbital speed at the time of disruption, which for Antares B is estimated at a few kilometers per second given the wide orbit. This is relatively modest by runaway star standards, but it would be supplemented by the kick imparted by the supernova ejector slamming into the companion's atmosphere. Runaway stars of this type have been observed elsewhere in the galaxy. Some of the fastest moving stars known are believed to be former companions of stars that exploded as supernovae. They travel through the galaxy at velocities far exceeding those of their neighbours, carrying in their chemical composition the telltale signatures of condensation by supernova ejecta. If we could analyse the atmosphere of such a star in sufficient detail, we could in principle read the chemical fingerprint of the supernova that set it free, reconstructing the nucleosynthesis of an explosion that occurred millions of years ago. Antares B, after the supernova, would carry exactly such a fingerprint, a forensic record of its companion's death, encoded in trace elements deposited on its surface by the blast. Antares does not exist in isolation within the galaxy. It is a member of the Upper Scorpius subgroup of the Scorpius-Centaurus OB association, one of the nearest regions of recent massive star formation to the Sun. This association is a loose grouping of young, hot, massive stars that were born from the same giant molecular cloud roughly 10 to 15 million years ago. Many of Antares' siblings have already exploded as supernovae. The evidence of their deaths surrounds us. The Rho-Ophiuchi cloud complex, one of the closest active star-forming regions to Earth, at a distance of roughly 400 light-years, is being shaped and illuminated by radiation from the upper Scorpius stars. The interstellar medium in this entire region of the galaxy has been sculpted by the blast waves of past supernovae, creating bubbles, filaments, and shells of hot gas that stretch across tens of degrees of the sky. Antares itself is embedded in this processed environment, surrounded by the remnants of its siblings' deaths. Its own supernova will add another chapter to this ongoing story of stellar feedback, the cycle in which massive stars enrich and reshape the interstellar medium, triggering new episodes of star formation from the compressed gas and dust left behind by their explosions. Now let us talk about what is actually happening inside this star, because the interior of Antares is where the real story unfolds. The core of Antares has long since exhausted its hydrogen. It burned through that fuel millions of years ago. Then it began fusing helium into carbon and oxygen. That stage lasted a shorter time. Then it began fusing carbon into neon and magnesium. Then neon into oxygen and magnesium. Then oxygen into silicon and sulfur. Each successive stage produces heavier elements, and each stage lasts a fraction of the time of the previous one. This acceleration is one of the most important features of massive stellar evolution, and it is worth spelling out in detail. Hydrogen burning lasted perhaps 8 to 12 million years. Helium burning lasted roughly 1 to 2 million years. Carbon burning lasts perhaps 1,000 years. Neon burning lasts about a year. Oxygen burning lasts a few months. And then comes silicon burning, the final stage, the stage where silicon is fused into iron, nickel, and other iron group elements. This stage lasts approximately 1 day. In some models, it lasts only hours. The acceleration is exponential. Each stage is roughly 100 to 1,000 times shorter than the previous one. And when the core becomes iron, fusion stops. Iron cannot be fused to produce energy. It is the end of the nuclear road. The core, no longer supported by the outward pressure of fusion, collapses under its own gravity at roughly 1/4 the speed of light. In less than a second, the inner core compresses from a volume roughly the size of the Earth to a sphere about 20 kilometers across. A neutron star, the density becomes so extreme that a teaspoon of this material would weigh roughly 6 billion tons. The atoms themselves are crushed out of existence. Protons merge with electrons to form neutrons. The entire mass of the core, 1.5 times the mass of the Sun, is compressed into a sphere smaller than a city. The outer layers of the star, still falling inward, slam into this suddenly rigid core and bounce. A shockwave races outward. Neutrinos, trillions upon trillions of them, blast through the collapsing material and deposit enough energy to revive the stalled shockwave. And then the star explodes. A supernova, a Type II supernova, an event so energetic that for a few weeks, this single dying star will outshine its entire host galaxy. It will release more energy in those few seconds of core collapse than the Sun will produce in its entire 10 billion year lifetime. This is the fate of Antares, not a possibility, a certainty. The only question is when. The modern study of Antares accelerated dramatically in the 21st century. In 2016, a team using the Very Large Telescope Interferometer at the European Southern Observatory in Chile produced the most detailed image ever taken of a star other than the Sun. That star was Antares. The image revealed enormous convective cells on its surface, vast upwellings of hot gas rising from deep within the star, each one larger than the entire orbit of Earth around the Sun. The surface was not smooth. It was turbulent, chaotic, alive with motion. Material was being flung off the surface at velocities that surprised the observers. The star was actively losing mass, shedding its outer layers into space, at a rate that astonished even those who expected to find significant mass loss. In 2017, a team led by Keiichi Onaka published observations of the extended atmosphere of Antares using the Atacama Large Millimeter Array, known as ALMA. They found that the star's atmosphere extends far beyond what models predicted, reaching out to roughly 12 stellar radii, an enormous envelope of turbulent gas that defied existing convection models. Something was driving gas to higher altitudes and greater velocities than theory could explain. The implication was clear and unsettling. Our understanding of how red supergiants behave, how they lose mass, and how they prepare for death, was incomplete. Something fundamental was missing from the models. These findings were not isolated curiosities. They pointed to a fundamental gap in our theoretical understanding of how massive stars behave in the final stages of their lives. For decades, stellar evolution models had treated mass loss from red supergiants as a relatively well-understood process, driven primarily by radiation pressure on dust grains that form in the cool outer atmosphere. The dust grains absorb stellar radiation, gain momentum, and drag the gas along with them, creating a steady outflow that strips material from the star over time. This mechanism works reasonably well for lower-mass giant stars on the asymptotic giant branch, but the ALMA observations of Antares suggested that something additional and more powerful was at work. The gas was being accelerated to velocities and altitudes that dust-driven winds alone could not explain. Convective motions, sound waves, shocks from pulsation, or perhaps magnetic fields were contributing to the mass loss in ways that the standard models had not accounted for. A separate study using the Very Large Telescope in 2014 had already hinted at this problem. Researchers mapping the velocity field of the gas around Antares found evidence of large-scale turbulent motions extending well beyond the photosphere, the visible surface of the star. These motions were not random. They showed structure, with upwelling and downwelling regions that suggested organized convective flows on scales comparable to the stellar radius itself. The energy contained in these flows was substantial, more than enough to lift material against the star's gravity and launch it into the circumstellar environment at high speed. This was a clue that the mass loss mechanism was far more dynamic, far more chaotic, and far more complex than the simple dust-driven wind model had assumed for decades. Something is wrong with our assumptions. This discovery mattered because the mass loss rate of a red supergiant before it explodes directly affects the nature of the explosion and its aftermath. A star that has shed a great deal of mass will produce a different type of supernova than one that retains most of its envelope. The amount of material surrounding the star at the moment of detonation determines how bright the explosion will appear, how much material is ejected, what kind of remnant is left behind, and how the blast wave will interact with the circumstellar environment. If Antares is losing mass faster than models predict, then our predictions about its death may need fundamental revision. And this is where the story takes its deepest turn, because Antares is not just a dying star. It is a laboratory. It is the closest red supergiant that we can study in exquisite detail before it explodes. Its position in the southern sky makes it accessible to the most powerful ground-based telescopes on Earth, including those in Chile's Atacama Desert, which enjoy some of the clearest, driest, most stable atmospheric conditions anywhere on the planet. Antares has been observed with a Very Large Telescope, the Atacama Large Millimeter Array, the Gemini Observatory, and numerous other facilities. It is one of the most intensely monitored stars in the sky, and yet, for all this attention, we still cannot answer the most fundamental question. How long does it have? The honest answer is that we do not know. We know that it has moved beyond core hydrogen burning. We know that it has moved beyond core helium burning. We are relatively confident that it is somewhere in the advanced nuclear burning stages, possibly carbon or neon burning, possibly even further along. But pinning down the exact stage is extraordinarily difficult because the external appearance of a red supergiant changes very little during these final stages. The surface remains red. The luminosity remains roughly constant. The size fluctuates but does not dramatically shift. From the outside, a red supergiant that has 1,000,000 years left looks almost identical to one that has 1,000 years left, or 100, or 1. That question, as we shall see, is far more troubling than it sounds. And the answer, or rather the absence of an answer, leads us into the heart of the problem. The death of a star like Antares is not a gradual dimming. It is not a slow fading into darkness. It is a catastrophic, violent, universe-shaking event that unfolds in stages, each more extreme than the last, beginning with a process so sudden and so total that it remains one of the most dramatic phenomena in all of physics: core collapse. To understand core collapse, we need to understand what has been holding the star up for its entire life. Every star exists in a state of tension, a balance between two opposing forces. Gravity pulls everything inward, trying to compress the star into the smallest possible volume. Radiation pressure, generated by nuclear fusion in the core, pushes everything outward, trying to blow the star apart. For millions of years, these two forces are in approximate equilibrium. The star neither collapses nor expands catastrophically. It burns, it shines, it exists in a precarious but stable standoff. This balance is called hydrostatic equilibrium, and it is the defining condition of a star's life. Every moment of a star's existence is a negotiation between gravity and pressure. Gravity never sleeps, gravity never relents. It is always there, always pulling, always waiting for the moment when the outward pressure falters. But this standoff depends entirely on fusion, and fusion depends on fuel. When the core of a massive star exhausts its hydrogen, it contracts slightly, heats up and begins fusing helium. When helium runs out, it contracts further, heats up more, and fuses carbon. Each new fuel ignites at a higher temperature than the last. Each stage produces less energy per unit of fuel consumed, and each stage lasts a shorter time. The star is climbing a ladder of desperation, burning through its options faster and faster, generating less and less net energy from each successive reaction, while gravity waits patiently for the moment when the fuel runs out entirely. It is a race that the star cannot win. Gravity always wins in the end. The internal structure of a massive star in its final stages is often compared to an onion. The core sits at the center, a dense ball of iron, or whatever the current burning fuel happens to be, surrounded by concentric shells of progressively lighter elements. Just outside the iron core is a shell where silicon is still fusing into iron. Outside that, a shell where oxygen is fusing into silicon. Outside that, neon fusing into oxygen. Then carbon, then helium, then hydrogen, each in its own shell, each at a different temperature and density, each burning at its own rate. The entire structure is nested, layered, and extraordinarily hot, with temperatures dropping from tens of billions of degrees at the center to a relatively cool 3,500 degrees at the surface. The journey from center to surface spans hundreds of millions of kilometers and crosses temperature ranges that span 7 orders of magnitude. It is, in a very real sense, multiple stars inside one another, each burning a different fuel, each existing at a different stage of nuclear evolution, all contained within a single gravitational envelope. This layered structure is not stable in a permanent sense. The boundaries between shells shift as fuel is consumed and ash accumulates. Convective plumes can dredge material from one layer into another, mixing fresh fuel into burning regions and altering the chemistry. Instabilities at shell boundaries can trigger episodes of enhanced burning that temporarily change the energy output and structure of the star. The whole system is dynamic, evolving, and increasingly precarious as the end approaches. Each new burning stage adds another layer to the onion, but also brings the core closer to the fatal threshold of iron. That moment arrives when the core is made of iron. Iron is the most tightly bound nucleus in nature. Fusing iron does not release energy. It consumes energy. It is an endothermic reaction, meaning it absorbs energy from its surroundings rather than contributing to them. When the core becomes iron, fusion ceases to provide the outward pressure that supports the star. The standoff ends. Gravity wins. And it wins absolutely. What happens next takes less than 1 second. The iron core, roughly 1.5 times the mass of the Sun, but compressed into a volume about the size of Earth, suddenly has no support. It collapses. The collapse is not gentle. It is not gradual. The core falls inward at speeds approaching 70,000 kilometers per second, roughly 1/4 the speed of light. In about 1/10 of a second, the core compresses from a sphere roughly 8,000 kilometers across to a sphere roughly 20 kilometers across. The density reaches 100 trillion times the density of water. Individual protons and electrons are squeezed together so forcefully that they merge into neutrons, releasing a flood of neutrinos in a process called neutronization. The temperature at the center reaches over 100 billion degrees Celsius, far hotter than the core of any main sequence star, hotter even than the centers of the most massive stars during normal nuclear burning. A neutron star is born, in a fraction of a second, from the ashes of an iron core that spent millions of years being constructed, element by element, reaction by reaction. In the very furnace that has now failed, the outer layers of the star, still falling inward under their own weight, slam into this suddenly rigid, incompressible neutron core. The impact generates a shockwave of unimaginable power. But here is a detail that many popular accounts leave out, a detail that puzzled astrophysicists for decades. The shockwave stalls. It does not have enough energy to blow through the entire star. It gets stuck, bogged down in the dense, infalling material above the core, losing energy as it struggles to push outward against the weight of the star's outer layers. For a fraction of a second, the explosion fails. The supernova, the most powerful explosion in the universe, stalls out like a car engine on a cold morning. And then the neutrinos arrive to save the day. The core collapse produces an almost inconceivable number of neutrinos, roughly 10 to the power of 58 of them, carrying away roughly 99% of the gravitational energy released by the collapse. That is approximately 3 times 10 to the power of 46 joules of energy, released in a matter of seconds, almost entirely in the form of these ghostly particles that normally pass through matter without interacting at all. A neutrino can pass through a light year of solid lead without being stopped. They are, under normal circumstances, the least interactive particles in the universe. But at the densities inside the collapsing star, even neutrinos begin to be absorbed. A tiny fraction of them, perhaps 5%, deposit their energy into the stalled shockwave. And that tiny fraction, 5% of 99% of the most energetic event in the universe, is enough. The shockwave revives. It accelerates. It tears through the outer layers of the star at tens of thousands of kilometers per second, and the star explodes. This is a Type II supernova. This is how Antares will die, not with a whimper, with a scream that echoes across the galaxy. The energy released is staggering. A typical Type II supernova radiates roughly 10 to the power of 44 joules in visible light alone, making it temporarily as bright as 10 billion suns. But the visible light is only 1% of the total energy. The remaining 99% is carried away by neutrinos, invisible to the eye but detectable by specialized underground detectors here on Earth. If Antares were to explode today, the neutrino detectors at facilities like Supergiant in Japan, IceCube at the South Pole, and the Sudbury Neutrino Observatory in Canada would register a burst of detection so intense that it would be immediately recognizable as a galactic supernova. In fact, these detectors have been waiting for exactly this signal for decades. An automated alert system called the Supernova Early Warning System, or SNEWS, links these detectors together, so that a confirmed detection would trigger alerts to observatories around the world within minutes, possibly before the visible light of the explosion even reaches us. That last detail deserves emphasis. The neutrinos would arrive first. They travel at nearly the speed of light, but are released during the core collapse, before the shock wave reaches the surface of the star. The visible light of the supernova emerges only when the shock wave breaks through the stellar surface, which can take hours after core collapse for a star as large as Antares. This means that we could receive a neutrino alert and know, with scientific certainty, that Antares has exploded hours before we see any change in the last day. We would know, we would wait. We would point every telescope on Earth and in orbit at Scorpius, and then, slowly, Antares would begin to brighten. What would it look like from Earth? At a distance of 550 light-years, the supernova would reach an apparent magnitude of roughly -15 to -17. For reference, the full moon has an apparent magnitude of roughly -12.7. This means Antares, at peak brightness, would be somewhere between 10 and 100 times brighter than the full moon. It would be easily visible in broad daylight, a piercing point of white-blue light hanging in the daytime sky like a second, smaller sun. At night, it would cast sharp shadows. It would illuminate the landscape with a cold, bluish-white light, profoundly different from the warm red glow we associate with the star today. The color shift would be dramatic and immediate. The explosion compresses and heats the ejected material to temperatures of tens of thousands of degrees, shifting the peak emission from the deep red of the supergiant to the blue-white of a violent detonation. This brightness would persist for weeks. The light curve of a Type IIp supernova, the most common subtype, shows a plateau lasting roughly 100 days, during which the brightness remains relatively constant as the expanding shell of hydrogen recombines and radiates. For roughly 3 months, Antares would dominate the night sky. It would be the topic of every news broadcast, every conversation, every prayer. Then it would begin to fade, powered now by the radioactive decay of nickel-56 into cobalt-56 and eventually iron-56. Over the following year, the brightness would decline exponentially. Within 2 to 3 years, the remnant would fade below naked eye visibility. But the expanding shell of debris, the supernova remnant, would continue to glow for thousands of years, spreading across an ever larger region of space, enriching the interstellar medium with heavy elements forged in the explosion. And it gets worse. The explosion itself, as dramatic as it would appear from Earth, is only part of the story. The real concern lies in what the supernova would do to the space around it. A supernova releases not just light, but a blast wave of material, a shell of gas expanding at roughly 3 to 10% the speed of light, carrying with it heavy elements, radioactive isotopes, and an enormous flux of high-energy particles known as cosmic rays. This blast wave would eventually sweep through the region of space surrounding Antares, creating a supernova remnant similar to the Crab Nebula or the Veil Nebula, but far closer to Earth than any remnant we have ever observed at the time of its creation. At 550 light-years, Earth is almost certainly safe from the most dangerous effects. The commonly cited danger threshold for supernova radiation, particularly the gamma rays and cosmic rays that could affect a planet's atmosphere, is roughly 25 to 50 light-years. At that range, a supernova could strip away a significant fraction of the ozone layer, exposing the surface to increased ultraviolet radiation with potentially devastating consequences for life. Some paleontological evidence suggests that mass extinction events in Earth's history may have been triggered or worsened by nearby supernovae, though the evidence remains debated. At 550 light-years, the inverse square law reduces the radiation flux by a factor of roughly 120 to 480 compared to the danger threshold. The ozone layer would be fine. The biological effects on Earth would be negligible. We would see the show, we would not feel the heat. But here's the problem. We are not certain of the distance to Antares. The commonly cited value of 550 light-years comes from Hipparcos satellite measurements of its parallax, the apparent shift in position caused by Earth's orbital motion around the Sun. But Antares is a difficult target for parallax measurements. It is a semi-regular variable star, meaning its brightness and apparent diameter fluctuate over periods of months to years. Its surface is covered in enormous convective cells that shift the photocenter, the apparent location of the star's brightest point, in unpredictable ways. The Hipparcos parallax for Antares carries a significant uncertainty, and different analyses have placed the star anywhere from roughly 520 to 620 light-years away. The revised Hipparcos reduction by Floor van Leeuwen in 2007 gave a distance of roughly 550 light-years, with an uncertainty of about 70 light-years in either direction. There is another dimension to the distance problem that is worth exploring. The Gaia Space Observatory, launched by the European Space Agency in 2013, has revolutionized our knowledge of stellar distances by measuring parallaxes for nearly 2 billion stars with unprecedented precision. But Gaia struggles with the very brightest stars, and Antares is one of the brightest in the sky. The star saturates Gaia's detectors, making precise astrometric measurements difficult. Early Gaia data releases did not include reliable parallaxes for Antares, and while subsequent data releases have improved the situation somewhat, the parallax measurement for a star this bright and this angularly large remains challenging. The combination of detector saturation, photocentric variability, due to the enormous convective cells on the surface, and the difficulty of modeling a resolved stellar disk rather than a simple point source means that even our best space-based astrometry has not definitively pinned down the distance to Antares. Radio interferometry offers an alternative approach. Very long baseline interferometry, or VLBI, can measure the positions of radio sources with extraordinary precision, potentially providing independent distance estimates for nearby stars. But Antares is not a strong radio source under normal conditions, and the complex circumstellar material around it complicates the identification of a clean reference point for position measurement. Some progress has been made using observations of the circumstellar material itself, and measurements of the proper motion of Antares across the sky have been combined with radial velocity measurements to determine its three-dimensional space velocity through the galaxy. But the absolute distance remains the weakest link in the chain of knowledge about this star. The implications of distance uncertainty cascade through every other parameter we try to measure. Luminosity scales as the square of the distance. If the true distance is 10% larger than our best estimate, the luminosity is 21% larger, and the inferred mass is correspondingly higher. If the distance is 10% smaller, the star is less luminous, less massive, and possibly in a less advanced evolutionary state than we currently believe. This kind of systematic uncertainty is the quiet background noise against which all of our interpretations of Antares must be evaluated. The distance uncertainty affects more than just our safety calculations. It affects our ability to determine the star's luminosity, its mass, and therefore our predictions of how it will die. If the star is closer than we think, it is less luminous than we think, and possibly less massive. If it is farther, the opposite is true. The mass of Antares is particularly uncertain, and mass is the single most important parameter for determining the fate of a massive star. Estimates for the mass of Antares A range from about 11 solar masses to more than 14.3 solar masses, with some analyses suggesting values as high as 17 or 18 solar masses, depending on the evolutionary models used. The uncertainty arises from the difficulty of measuring the mass of a star that is not in a closed binary system, where orbital dynamics can provide precise gravitational measurements. Antares B orbits at such a large distance, with an orbital period estimated at roughly 870 years, that only a small arc of its orbit has been observed since telescopic observations began. The resulting mass estimates are model-dependent and carry significant error bars. Different groups using different methods have arrived at different answers, and there is no consensus on a single best value. Why does mass matter so much? Because the mass of the core at the moment of collapse determines what kind of remnant is left behind. If the core mass is below roughly 2.1 solar masses, the remnant will be a neutron star, an incredibly dense but stable object held up by neutron degeneracy pressure, the quantum mechanical resistance of neutrons to being compressed any further. If the core mass exceeds this limit, known as the Tolman-Oppenheimer-Volkoff limit, no known force can halt the collapse. The remnant becomes a black hole, a puncture in the fabric of space-time from which nothing, not even light, can escape. For Antares, the most likely outcome is a neutron star. Models suggest that a star with an initial mass in the range of 11 to 17 solar masses will typically produce a neutron star remnant, though the exact boundary depends on how much mass the star loses through stellar winds before it explodes, and on the details of the explosion mechanism itself. But the possibility of a black hole cannot be entirely ruled out, particularly if the explosion fails, a scenario known as a failed supernova, where the shockwave does not successfully eject the outer layers, and the entire star collapses into a black hole with only a faint transient or no visible explosion at all. Failed supernovae are not hypothetical. In 2015, astronomers reported the disappearance of a red supergiant star in the galaxy NGC 6946. The star, which had been monitored as part of a survey specifically looking for failed supernovae, had a luminosity and temperature consistent with a red supergiant of roughly 25 solar masses. It brightened slightly over a few months, then vanished. No supernova was observed, no brightening, no blast wave. The star simply ceased to exist as a visible object. The most likely explanation was that the star's core collapsed directly into a black hole, swallowing the entire star without producing a successful explosion. This was the first strong observational evidence that some massive stars die not with a bang, but with a silent swallowing of their own matter. Could this happen to Antares? It is unlikely, but not impossible. The current best estimates place Antares in the mass range where a successful supernova and neutron star formation are the expected outcomes. But our models of core collapse are still incomplete. The physics of the neutrino-driven mechanism, the interaction between the shock wave and the infalling material, the role of rotation and magnetic fields in shaping the explosion, all of these remain areas of active research and considerable debate. Three-dimensional simulations of core collapse supernovae have only recently become sophisticated enough to reliably produce explosions, and they still struggle with certain mass ranges and metallicities. The computational demands are enormous. A single three-dimensional simulation of a core collapse supernova can require millions of processor hours on the world's fastest supercomputers. The history of supernova observation from within our galaxy is thinner than most people realize. The last supernova visible to the naked eye in our galaxy was Kepler's supernova in 1604, observed by Johannes Kepler and other astronomers across Europe and Asia. That was over 400 years ago. Before that, Tycho Brahe observed one in 1572, a supernova that was bright enough to be visible in daylight and that shook the prevailing Aristotelian belief in the immutability of the heavens. Before that, Chinese and Islamic astronomers recorded the supernova of 1054, which created the Crab Nebula. In the entire recorded history of human civilization, spanning at least 5,000 years, we have observed fewer than 10 galactic supernovae with certainty. We have never observed a nearby supernova with modern instruments. Not once. The last time a supernova was visible to the naked eye anywhere in the vicinity of our galaxy was in 1604. That means that no living human being has ever seen a galactic supernova. No modern astronomer has observed one with even the most basic telescopic equipment, let alone with the sophisticated instruments available today. Our entire understanding of the supernova mechanism, the physics of core collapse, the neutrino-driven explosion, the nucleosynthesis of heavy elements, has been constructed from theoretical models, computer simulations, laboratory nuclear physics experiments, and observations of supernovae in distant galaxies. This is a remarkable situation. It is as if seismologists had never directly witnessed a major earthquake and had to deduce everything about seismic physics from the faint tremors detected thousands of kilometers away. The models are good, the physics is well grounded, but the direct observational test, the ultimate validation of our understanding, has never been performed for a galactic supernova in the era of modern instrumentation. This absence shapes our science in ways that are not always fully appreciated. When we model the light curve of a Type II supernova, we compare our predictions to observations of supernovae in galaxies millions of light-years away. But those distant observations are limited by their very distance. We can measure the total brightness, the color evolution, the spectral features, and the expansion velocity of the ejecta. But we cannot resolve the spatial structure of the explosion. We cannot map the asymmetries in the expanding shell. We cannot watch the shock wave break through the stellar surface in real time. We cannot correlate the neutrino signal with the electromagnetic signal on a second-by-second basis. All of these things would be possible with a nearby supernova. All of them would test our models in ways that have never been tested. And Antares, at 550 light-years, would provide exactly that opportunity. Every single thing we know about supernovae from direct observation comes from events in other galaxies, at distances of millions or tens of millions of light-years, too far to study in the kind of fine detail that a nearby event would allow. Supernova 1987A, the supernova in the Large Magellanic Cloud that was detected in February of 1987, was the closest observed supernova in the modern era, and even that was 168,000 light-years away. It provided invaluable data, including the first-ever detection of neutrinos from a supernova, but it was still too distant for the level of detailed study that modern instruments could achieve. Antares would change everything. A supernova at 550 light-years, observed with the full suite of modern instruments, ground-based and space-based telescopes spanning the electromagnetic spectrum from radio to gamma rays, neutrino detectors on multiple continents, gravitational wave observatories at design sensitivity, would be the astronomical event of the millennium. It would provide data that would transform our understanding of stellar death, nucleosynthesis, neutron star formation, the nuclear equation of state, and the origin of heavy elements. It would be, without exaggeration, the single most important astronomical event in human history, and we cannot predict when it will happen. We can only watch and wait. Some researchers have attempted to narrow the window by studying the pulsation patterns of Antares. Red supergiants pulsate, expanding and contracting over periods of months to years, and these pulsations are driven by processes in the stellar envelope that may carry faint echoes of deeper activity. Antares is classified as a semi-regular variable, with a primary pulsation period of roughly 1,733 days, about 4.7 years. Attempts to connect these pulsation characteristics to the interior evolutionary state have produced ambiguous results. The pulsations tell us about the envelope. They tell us nothing definitive about the core. But here's what makes this truly terrifying. The lack of a clear warning signal means that the supernova, when it comes, will arrive with almost no advance notice in any conventional sense. The neutrino burst from core collapse will arrive hours before the visible explosion, giving us perhaps 6 to 12 hours of warning. But there will be no slow build-up over years or decades. No gradual brightening, no unmistakable sign that the end is imminent. Antares could look exactly as it does tonight, red, steady, quiet, and then 12 hours later be brighter than the moon. The question of when Antares will explode has driven several distinct lines of scientific investigation, each approaching the problem from a different angle and each revealing both insights and frustrations. Let us walk through the 5 most significant attempts to predict or constrain the death of this star, examining what each has revealed and where each has fallen short. The first approach is stellar evolution modeling. This is the most fundamental and most widely used method. Astrophysicists construct theoretical models of stars with initial masses and compositions similar to Antares, then simulate their evolution from birth to death using sophisticated computer codes that track nuclear burning, convection mass loss, rotation, and other physical processes. These codes, such as the MESA code, which stands for Modules for Experiments in Stellar Astrophysics, have become remarkably powerful in recent decades. They incorporate thousands of nuclear reactions, detailed equations of state for matter at extreme temperatures and densities, and increasingly realistic treatments of turbulence, mixing, and angular momentum transport. The scientific community has invested decades of effort into building and refining these tools, and they represent some of the most complex software in all of science. The models broadly agree on the narrative arc. A star of roughly 12 to 15 solar masses will spend 8 to 12 million years on the main sequence burning hydrogen, then evolve through the red supergiant phase over a period of roughly 1 to 2 million years, during which it burns helium, carbon, neon, oxygen, and finally silicon before collapsing. The models tell us where Antares sits on the Hertzsprung-Russell diagram, the fundamental plot of stellar luminosity versus surface temperature that astronomers use to classify and compare stars. They tell us that Antares' current position on this diagram is consistent with a star in the advanced stages of nuclear evolution, somewhere past core helium burning and into the realm of carbon burning or beyond. But the models fail in a critical way. They cannot tell us which specific burning stage Antares is in right now. The reason is that the external properties of the star, its surface temperature, luminosity, and radius, change very little during the transition from carbon burning to neon burning to oxygen burning to silicon burning. These stages are happening deep in the core, beneath hundreds of millions of kilometers of opaque gas, and their influence on the surface is minimal. A star that is burning carbon in its core looks almost exactly like a star that is burning silicon in its core. From the outside, the difference is undetectable with current observational capabilities. The numbers are striking. Carbon burning lasts roughly 1,000 years. Neon burning lasts roughly 1 year. Oxygen burning lasts a few months. Silicon burning lasts about a day. If Antares is currently in its carbon burning phase, it has perhaps 1,000 years left. If it is in its neon burning phase, it might have roughly a year. If it is in its oxygen burning phase, it has months. If it has already reached silicon burning, it has hours. And our models, despite their extraordinary sophistication, cannot distinguish between these scenarios based on the available observational data. The surface of the star does not know, in any meaningful sense, what the core is doing. This is not a failure of effort or intelligence. It is a fundamental limitation of the physics. The core is opaque. The photons generated in the core are absorbed and re-emitted billions of times before they reach the surface, losing all information about their origin in the process. The surface is thermally and dynamically decoupled from the core during the advanced burning stages. The timescales of the final burning stages are so short, by astronomical standards, that they represent a vanishingly small fraction of the star's total lifetime. Finding Antares in its last 1,000 years is like finding a specific grain of sand on a beach. Finding it in its final day is like finding a specific atom in that grain of sand. There is a further complication that makes the modeling problem even more challenging than this summary suggests. The treatment of convection in stellar evolution codes is approximate by necessity. Convection, the physical process by which hot gas rises and cool gas sinks, is the primary mechanism for transporting energy and mixing chemical elements in the interiors of massive stars. It occurs on scales ranging from meters to millions of kilometers, and it involves turbulent flows that are inherently three-dimensional, time-dependent, and chaotic. Fully resolving convective flows in a stellar interior would require computational grids with billions of resolution elements and time steps of seconds, sustained over millions of years of stellar evolution. This is utterly beyond current or foreseeable computing capabilities. Instead, modelers use approximate prescriptions, the most common being a framework called mixing length theory, which reduces the three-dimensional turbulent flow to a one-dimensional parameterization involving a single adjustable parameter, the mixing length. This parameter is typically calibrated against observations of the Sun and then applied, with considerable uncertainty, to stars of vastly different mass, composition, and evolutionary state. The choice of mixing length parameter, and more broadly the treatment of convective boundaries, overshooting and semi-convective mixing, has profound consequences for the predicted evolution of massive stars. Small changes in these parameters can alter the predicted duration of the red supergiant phase by factors of 2 or more. They can change the predicted mass of the core, the chemical composition of the burning shells, the mass loss rate, and ultimately the type and energy of the supernova. Different research groups using different codes with different convective prescriptions regularly arrive at different answers for stars of the same initial mass. This is not a reflection of error or incompetence. It is a reflection of the genuine physical uncertainty in how convection operates in stellar interiors, an uncertainty that decades of effort have reduced but not eliminated. The second approach involves astroseismology, the study of stellar oscillations. Just as geologists study earthquakes to learn about Earth's interior, astrophysicists study the oscillations of stars to infer their internal structure. A star like the Sun oscillates in millions of different modes, each one a standing wave that probes a different depth and region within the star. By measuring these oscillations and comparing them to theoretical predictions, scientists can construct detailed models of the interior, including the size and density of the core, the extent of convective zones, and the chemical composition at various depths. Astroseismology has been spectacularly successful for main sequence stars and red giants. The Kepler Space Telescope, launched in 2009, and its successor, TESS, the Transiting Exoplanet Survey Satellite, have measured oscillations in thousands of stars with exquisite precision, revealing the internal rotation rates, core hydrogen fractions, and evolutionary states of stars across the galaxy. For these stars, astroseismology provides a window into the interior that is almost magical in its clarity. You can determine the age of a star from its oscillation frequencies with a precision that no other method can match. But for red supergiants, the technique faces severe challenges. Red supergiants oscillate, but their oscillations are dominated by low-frequency, large amplitude modes, driven by turbulent convection in the outer envelope. These modes are irregular, noisy, and difficult to interpret. The clean, orderly pattern of oscillation frequencies that makes astroseismology so powerful for solar-type stars is largely absent in supergiants. Instead, what we observe is a messy, variable, quasi-periodic signal that reflects the chaotic surface dynamics rather than the ordered structure of the deep interior. It is like trying to hear a whispered conversation in a hurricane. The signal is there, perhaps, but the noise overwhelms it. Attempts to apply astroseismology to Antares have yielded some results, but they are frustratingly limited. The primary pulsation period of roughly 4.7 years has been confirmed by multiple independent studies, and secondary periods have been tentatively identified at shorter timescales. Some researchers have attempted to use these periods to constrain the mass and evolutionary state of the star, with results that are broadly consistent with what we already know from evolutionary models, but that do not provide the precision needed to identify the specific core burning stage. The oscillation modes of red supergiants are simply too chaotic and too poorly understood to serve as reliable diagnostics of the deep interior, at least with current theoretical frameworks and observational techniques. The challenge with red supergiant astroseismology goes even deeper than the noise problem. Even in principle, the oscillation modes of these stars are fundamentally different from those of smaller stars. In the Sun and in red giant branch stars, the oscillation modes are acoustic modes, pressure waves that propagate through the interior and reflect off the surface, creating standing wave patterns with well-defined frequencies. These frequencies depend on the sound speed profile inside the star, which in turn depends on the temperature, composition, and density structure. By measuring many mode frequencies, scientists can invert the data to reconstruct the internal structure with remarkable precision. In red supergiants, the situation is much more complicated. The stars are so large, and their outer envelopes are so extended and tenuous that the acoustic modes have very long periods and very large amplitudes. The convective motions in the envelope are comparable in scale and energy to the oscillation modes themselves, making it difficult to separate pulsation from convection. The boundary between the star and its extended atmosphere is not sharp but gradual, making it unclear where the oscillation boundary conditions should be applied. And the strong coupling between convection and pulsation means that the modes are not clean sinusoidal oscillations but complex, nonlinear, chaotically modulated variations that resist the kind of precise frequency analysis that has made astroseismology so successful for other types of stars. Some theoretical studies have explored the possibility that gravity modes, oscillations driven by buoyancy forces rather than pressure forces, might propagate through the deep interior of red supergiants and carry information about the core structure to the surface. Gravity modes are well known in solar physics, where they are predicted to exist but have never been unambiguously detected because they are trapped below the convective zone and have extremely small amplitudes at the surface. In a red supergiant, the convective envelope is much larger, and the question of whether gravity modes can propagate through it to reach the surface is still debated. If they can, they would in principle carry information about the density and composition profile near the core, which is exactly what we need to determine the nuclear burning stage. Recent theoretical work has suggested that the final stages of nuclear burning might produce detectable changes in the pulsation pattern, particularly during silicon burning, when the rapid energy release in the core could excite gravity modes, oscillations that propagate through the interior of the star and that are sensitive to the density profile near the core. These gravity modes would be of very low frequency and very low amplitude, making them extremely difficult to detect. Even the most optimistic assessments suggest that we might detect a change in pulsation behavior only hours to days before core collapse, which is essentially no warning at all in practical terms. The star would have to already be in its death throes before the pulsations told us anything useful. The third approach is neutrino detection. As mentioned earlier, the core collapse of a massive star produces an enormous burst of neutrinos, and modern neutrino detectors are capable of detecting this burst from across the galaxy. But this approach provides warning only at the very end, in the final seconds of the star's life. It is not a predictive tool in the usual sense. It is an alarm. The Supernova Early Warning System, (SNIRS), is designed to detect the neutrino burst and alert observatories worldwide within minutes. But it cannot tell us when the burst will come. It can only tell us that it has already happened. The alarm sounds after the event, not before. There is, however, a more subtle possibility that has received increasing attention in recent years. Before core collapse, during the advanced burning stages, the core produces a steady stream of neutrinos from the nuclear reactions. These pre-supernova neutrinos are far less energetic than the collapsed neutrinos, and they are far fewer in number. But they are not zero. During neon burning, and especially during silicon burning, the neutrino luminosity of the core increases dramatically. The core becomes, in effect, a neutrino furnace, producing particles at a rate that dwarfs the neutrino output of all earlier burning stages. Some researchers have suggested that next-generation neutrino detectors might be able to detect this increased flux from a star as close as Antares, potentially providing hours or even a day or two of warning before the final collapse. The Camelon detector in Japan, the planned Juno detector in China, and other next-generation facilities have been discussed as potential instruments for pre-supernova neutrino detection. The sensitivity requirements are extreme. The expected signal from a star 550 light-years away during silicon burning is only a few neutrinos per day above the background rate, a signal so faint that it would require years of quiet observation to establish a baseline and then careful statistical analysis to identify an increase above the noise. This is not currently feasible with existing technology, though advances in detector sensitivity and analysis techniques may make it possible within the coming decades. It remains one of the most tantalizing possibilities on the horizon of stellar astrophysics. The importance of neutrino detection for a nearby supernova cannot be overstated. When supernova 1987A occurred in the Large Magellanic Cloud, the neutrino detectors of that era, Kamiokande 2 in Japan and the Irvine, Michigan Brookhaven detector in Ohio, together detected a grand total of roughly 20 neutrinos from the event. 20 particles detected over a span of roughly 13 seconds from a star 168,000 light-years away. Those 20 neutrinos confirmed several key predictions of supernova theory and earned Masatoshi Koshiba a share of the 2002 Nobel Prize in Physics. They demonstrated that core collapse supernovae produce neutrinos in roughly the quantities and energies that theory predicted. They confirmed that the collapse occurs over a timescale of seconds, not minutes or hours, and they constrained the mass of the neutrino itself, showing that it is either zero or extremely small. Now consider what a supernova at 550 light-years, roughly 300 times closer, would produce. The neutrino flux scales as the inverse square of the distance, so a supernova at the distance of Antares would deliver roughly 90,000 times more neutrinos per unit area than supernova 1987A. Modern detectors are also vastly more sensitive than their 1987 counterparts. Super Kamiokande alone would detect roughly 10,000 neutrinos from such an event. IceCube, despite being designed primarily for high-energy astrophysical neutrinos, would detect the supernova neutrinos as a collective increase in background rate across its thousands of optical modules, effectively turning the entire Antarctic ice sheet into a supernova detector. The combined data from all operating neutrino facilities would provide a second-by-second record of the core collapse, the neutron star formation, and the cooling of the proto-neutron star, with enough statistics to measure the energy spectrum, flavor composition, and temporal structure of the neutrino emission with extraordinary precision. This is not speculation. This is straightforward physics. The detectors exist. The calculations have been done. All that is missing is the supernova. The fourth approach is spectroscopic and imaging monitoring. By carefully analyzing the spectrum of light from Antares, and by directly imaging its surface and extended atmosphere, astronomers can measure the chemical composition, temperature, density, velocity structure, and mass loss rate of the material in and around the star. Changes in these properties over time might reveal clues about the evolutionary state of the star or about processes occurring near the core. Antares has been spectroscopically monitored for decades by observatories around the world. Its spectrum shows the characteristic features of a cool M-type supergiant, including strong molecular absorption bands of titanium oxide, vanadium oxide, and other molecules that form in the relatively cool outer atmosphere. The spectrum also shows evidence of ongoing mass loss, including emission lines from ionized gas in the extended atmosphere and circumstellar envelope. Studies have documented changes in the strength, shape, and velocity profiles of certain spectral features over timescales of months to years, likely related to the pulsation cycle and surface convective activity. The breakthrough imaging observations from 2016 and 2017, using the Very Large Telescope Interferometer and ALMA respectively, added a new dimension to this work. For the first time, astronomers could see the surface of Antares directly, resolving individual convective cells and mapping the velocity field of the atmosphere in 3 dimensions. These observations revealed a star that is far more dynamic and far more complex than models had predicted. The convective motions are vigorous, asymmetric, and time variable. The mass loss is not uniform, but concentrated in specific regions and directions. The extended atmosphere has properties that no existing model can fully reproduce, but connecting these surface and atmospheric observations to the state of the deep interior is like trying to diagnose a patient's internal organs by studying the texture of their skin. There are correlations, hints, suggestions, but there is no direct line of inference. A change in the convective pattern might reflect a change in the energy flux from the core, or it might reflect a purely local hydrodynamic instability with no connection to the nuclear burning below. Separating signal from noise in this context is one of the grand challenges of observational stellar astrophysics. One potentially promising diagnostic involves measuring the surface abundance of certain elements that are produced in specific nuclear burning stages, and that might be mixed to the surface by deep convective dredge-up episodes. If material from the carbon-burning shell or the neon-burning shell were mixed upward through the convective envelope to the surface, it would change the surface abundances of elements like sodium, aluminum, and magnesium in detectable ways. Some studies have reported evidence of such abundance anomalies in red supergiants, but the results are controversial. The abundance measurements carry large uncertainties, and the connection to specific core burning stages is heavily model dependent. The fifth and final approach is the statistical approach, which does not attempt to determine the exact evolutionary state of Antares at all, but instead estimates the probability of explosion within a given time frame based on known timescales and the assumption that we are observing the star at a random point in its red supergiant phase. The logic is straightforward but illuminating. The total duration of the red supergiant phase for a star of Antares' mass is roughly 1 to 2 million years. The final burning stages, from carbon burning to core collapse, last roughly 1,000 years. Therefore, the probability of Antares being in its final 1,000 years at any random moment is roughly 1,000 divided by 1 million, which gives a probability of about 1/10 of 1%. The probability of it being in its final year is roughly 1 in a million. The probability of it being in its final day is roughly 1 in 365 million. These numbers are reassuring at first glance. They suggest that an explosion in the near future is extraordinarily unlikely, but they carry important caveats that undermine their simplicity. First, they assume that we are observing Antares at a truly random point in its red supergiant evolution, which may not be valid. Second, they assume that the duration of the red supergiant phase is well constrained, which it is not. The theoretical estimates carry uncertainties of at least a factor of 2 and possibly larger. Different research groups using different evolutionary codes, with different treatments of mass loss, convection, and rotation, arrive at different estimates for the duration of this phase. Third, and most fundamentally, the statistical approach says nothing about when the explosion will actually occur. A 1 in a million probability means the event is unlikely in any given year, but it is guaranteed to happen at some point. Probability tells us about averages and expectations. It tells us nothing about the specific case. And here is a subtlety that often gets lost in popular discussions. The statistical approach assumes that Antares is equally likely to be at any point in its red supergiant phase. But if we had additional information that constrained its evolutionary state, the probabilities would shift dramatically. If spectroscopic, asteroseismic, or neutrino data suggested that Antares had already reached carbon burning, then the probability of explosion within the next 1,000 years would jump from 0.1% to nearly 100%. The statistical argument is only as strong as our ignorance. If we knew more, the numbers would change. And as we have seen, what we know is frustratingly, dangerously little. There is another complication that adds a layer of uncertainty beyond all of these approaches, and it concerns the role of binary interaction and circumstellar environment. Antares B orbits at a projected distance of 550 astronomical units, which is far enough that direct mass transfer is extremely unlikely. But the gravitational influence of a companion, even a distant one, can subtly perturb the mass loss geometry of the primary star, creating asymmetries in the circumstellar environment that affect how we interpret the observations. Wind-wind interactions between the outflows of the two stars can create shocks and density enhancements that complicate the picture further. Some models suggest that the presence of a companion could modulate the mass loss rate through tidal effects, though these effects are expected to be small at the current orbital separation. More importantly, from an observational standpoint, the circumstellar environment created by millions of years of mass loss will play a crucial role in shaping the supernova when it finally occurs. The blast wave from the explosion will not propagate into empty space. It will slam into the dense, structured circumstellar medium that Antares has been building around itself for millennia. This interaction can dramatically affect the brightness, duration, and spectral characteristics of the supernova, making it essential to understand the circumstellar environment in advance. Radio and infrared observations have mapped this environment in some detail, revealing shells, arcs, and filaments of material that record the history of mass loss. But interpreting these structures and predicting how they will interact with the supernova blast wave requires three-dimensional hydrodynamic simulations that are still in their early stages. There is an additional statistical consideration that adds nuance to this entire discussion. The galaxy contains roughly 1,000 red supergiants at any given time, give or take a factor of a few depending on how exactly you define the category. Of these, perhaps a few hundred are massive enough to eventually produce a core collapse supernova. The galactic supernova rate is estimated at roughly 1 to 3 per century, based on historical records and extragalactic surveys. This means that, on average, one of the current red supergiants in the galaxy explodes every 30 to 100 years. But with 1,000 candidates and no way to identify which one is closest to the end, the probability of any specific star being the next to go is roughly 1 in 1,000 per century. For Antares specifically, the odds are not meaningfully different from any other red supergiant of similar mass and evolutionary status. But this statistical average hides a crucial asymmetry. The impact of a supernova depends dramatically on its distance. A supernova 10,000 light-years away would be a fascinating astronomical event, visible to the naked eye as a new star for a few months, but ultimately a modest spectacle. A supernova 550 light-years away, the distance of Antares, would be one of the most dramatic events in human history. So, while the probability of Antares being the next galactic supernova is no higher than that of any other red supergiant, the consequences of it being the next one are vastly greater because of its proximity. This asymmetry between probability and impact is a familiar theme in risk analysis, and it applies to Antares with particular force. Let us pull these threads together. 5 major approaches have been applied to the question of when Antares will die. Stellar evolution models tell us the sequence of events but cannot identify the current stage. Astroseismology provides some constraints on mass and radius but cannot probe the deep core with current techniques. Neutrino detection offers a last-minute alarm but no advance warning with existing sensitivity. Spectroscopic and imaging observations reveal surface and atmospheric dynamics of unprecedented detail but cannot directly access the core state. And statistical arguments suggest the explosion is unlikely in the near future, but rest on assumptions that could be overturned by a single new measurement. Each approach has taught us something important. Each approach has run into walls, and the collective result is a picture of profound, unavoidable uncertainty. A star that we know will explode, a star that we have studied with extraordinary thoroughness using the most powerful instruments ever built by our species, a star whose death we cannot predict with any useful precision. This uncertainty is not a temporary inconvenience that will be resolved by the next observation or the next model. It is a structural feature of the problem, rooted in the opacity of stellar interiors and the brevity of the final burning stages. In the meantime, Antares continues to burn, it continues to pulsate, it continues to shed mass into the void, and somewhere deep in its core, hidden beneath hundreds of millions of kilometers of opaque gas, the final nuclear reactions are proceeding on a timetable that we cannot read toward an ending that we cannot postpone. There is something deeply disquieting about Antares that goes beyond the physics, beyond the numbers, beyond the models and the measurements. It is a feeling that emerges only when you sit with the full picture long enough for its implications to settle into your thinking. Antares is not just a star that will explode. It is a star that we can see with our own eyes, that we have named, that we have woven into our mythologies and our navigation tables and our seasonal calendars for thousands of years, and it will be destroyed. The heart of the scorpion will stop beating, not metaphorically, literally. The fusion reactions that make it glow will cease. The photons that carry its light to Earth will stop being produced. The red point that has anchored that constellation for the entire duration of human civilization will go dark, replaced briefly by a flash of unspeakable brilliance, and then by nothing at all. This is not science fiction. This is the inevitable, confirmed, physically certain outcome of the nuclear processes currently occurring within that star. There is no scenario in which Antares survives. There is no intervention. There is no alternative ending. No deus ex machina. The core will become iron. The iron will not fuse. The core will collapse. The star will explode. The light that has guided navigators and inspired poets and frightened astrologers for thousands of years will be replaced, briefly, by a blinding flash, and then by a slowly fading remnant, and then by nothing visible to the naked eye at all. The constellation Scorpius, as we know it, as every human being who has ever lived has known it, will lose its heart. Think about what that means in practical terms. For thousands of years, the red star at the center of the Scorpion's body has served as one of the most reliable landmarks in the southern sky. Polynesian navigators used it to cross thousands of miles of open ocean. Arabic astronomers calibrated their instruments against it. Greek and Roman poets wrote about it. Hindu astronomers named it Jestha and considered it one of the 27 lunar mansions. Aboriginal Australian astronomers incorporated it into songlines that mapped the continent. Every major civilization that could see the southern sky built stories, calendars, and navigation systems around this star. When it is gone, all of those traditions will refer to something that no longer exists. The sky will have a hole where Antares used to be. The remaining stars of Scorpius will still trace the shape of a scorpion, but the scorpion will be heartless, its most distinctive star replaced by empty darkness, or, for a few thousand years, by the faint glow of an expanding supernova remnant visible only through telescopes. Let that sink in. The permanence of the night sky is an illusion. We grow up looking at the stars and assuming they are eternal, fixed, unchanging. Ancient cultures called them the fixed stars, contrasting them with the wandering planets. This assumption of permanence is built into our language, our philosophy, our religious traditions. The stars are constants, the stars are reliable, the stars are forever, except they are not. They are fires, and fires burn out. Every single point of light in the night sky is a temporary phenomenon, a brief flare of nuclear energy in the vastness of cosmic time. The specific arrangement of stars that we call constellations is a snapshot, a brief alignment that exists only because we happen to be alive at this particular moment in cosmic history. 1,000,000 years ago, the constellations looked different. The stars were in different positions relative to each other. 1,000,000 years from now, they will be unrecognizable. Stars are born, they age, they die, and the patterns they form are as temporary as patterns in smoke. But the death of Antares is not an abstract, far-future possibility that we can safely file away alongside the heat death of the universe or the collision of the Milky Way with the Andromeda galaxy. It is a near-future certainty, where near future means somewhere between tomorrow and 100,000 years from now. On the timescale of human civilization, that is practically imminent. The entire recorded history of humanity, from the earliest Sumerian tablets to the present day, spans roughly 5,000 years. If Antares has even 100,000 years left, which is at the extreme upper end of estimates, then it has only 20 times the duration of human civilization remaining. 20. That is not a large number when you are counting multiples of everything we have ever built and recorded and remembered. And if it has less, if it is in its final 10,000 years, then it has only twice the duration of recorded history. If it is in its final 1,000 years, then it will explode within a time frame that some of the buildings standing today might still exist to witness. The human mind is poorly equipped to handle these timescales. We are designed by evolution to think in terms of days, seasons, and lifetimes. 1,000 years feels like eternity to a creature that lives for 80. 1,000,000 years is incomprehensible. But for a star like Antares, these are the relevant numbers. Its total lifespan is perhaps 12 million years. It has been a red supergiant for 1 to 2 million of those years. Its remaining time is somewhere between essentially 0 and 100,000 years. These are the numbers that define the uncertainty, and they are, by any human standard, deeply unsettling. Consider what it would mean if Antares exploded within the next century. The supernova would be visible to every human being on Earth who could see the sky. It would be visible during the day. It would be brighter than any astronomical event in recorded history, surpassing even the supernova of 1054, which Chinese astronomers recorded as a guest star that was visible in daylight for 23 days and visible at night for nearly 2 years. The Antares supernova, being closer and potentially more energetic, could be visible in daylight for weeks and visible at night for many months. It would be visible from every continent, every island, every ship at sea. No human being alive at that moment would be unaware of it. The social and cultural consequences of such an event would be profound and difficult to predict. History gives us some precedents, though none at this scale. When the supernova of 1054 appeared, Chinese court astronomers recorded it as an omen and debated its significance for the emperor. When Tycho's supernova appeared in 1572, it sparked a philosophical crisis in Europe, challenging the Aristotelian doctrine that the heavens were perfect and unchanging. These events occurred in cultures that interpreted the sky through frameworks of divine will and cosmic order. A supernova today would land in a very different context, one where billions of people carry cameras in their pockets, where social media can spread information and misinformation at the speed of light, and where scientific understanding coexists with persistent strains of mysticism, apocalypticism, and conspiratorial thinking. For the scientifically literate, the event would be awe-inspiring but comprehensible. They would understand that the explosion occurred 550 years ago, and that Earth is in no danger. For others, a star suddenly appearing in the daytime sky, brighter than the moon, casting shadows, outshining everything else at night, would be terrifying. Throughout history, unexpected celestial events have triggered waves of religious fervor, political upheaval, and social panic. A modern supernova would almost certainly generate all of these, alongside a simultaneous flood of scientific communication attempting to explain the phenomenon. It would be the first truly global astronomical event, witnessed simultaneously by every culture on Earth, and the range of human responses to it would tell us as much about ourselves as the event itself would tell us about stellar physics. The psychological impact would be profound and unpredictable. For the first time in modern history, humanity would witness the violent death of a star, not in a distant galaxy, not as a faint smudge on a photographic plate analysed by specialists, but as a blinding light in the sky, visible to every person on Earth who bothered to look up. The philosophical implications would ripple through every culture. The permanence of the heavens, a foundational assumption of nearly every human belief system ever constructed, would be visibly, undeniably shattered. A star that had been there since before the invention of writing would be gone, changed, different, exploded, and everyone would know it. Let that sink in. And there is another dimension to this that is rarely discussed, a dimension that involves the speed of light and the strange temporal displacement that it creates across cosmic distances. The light we see from Antares tonight left the star approximately 550 years ago, around the middle of the 15th century. When that light began its journey, the Byzantine Empire was in its final years. Gutenberg was developing his printing press. The great cathedrals of Europe were still being built. The civilizations of the Americas were flourishing in total ignorance of the existence of Europe. The light that reaches our eyes tonight has been traveling through the vacuum of space for all of that history, carrying information about a star that may no longer exist in the form we see it. If Antares exploded right now, this very moment, the light from that explosion would not reach us for 550 years. It would arrive around the year 2576. Conversely, and this is the part that induces a particular kind of vertigo, if the star exploded 550 years ago, in roughly 1476, we would be seeing the explosion arriving at Earth right now, or sometime in our near future. This is the cruel trick of cosmic distances. We are always looking into the past. The Antares we see tonight is the Antares of 1476. The Antares of today, of this very moment, is invisible to us. It could already be gone. The core could have already collapsed. The neutrinos could already be on their way. The light of the explosion could be expanding outward through space at this very moment, a sphere of brilliance racing toward us at 300,000 kilometers per second, and we would have absolutely no way of knowing, not until it arrives. This temporal displacement creates a strange philosophical situation that has no parallel in everyday human experience. It is possible, though statistically improbable, that Antares no longer exists, that the heart of the scorpion stopped beating centuries ago, and the news simply has not reached us yet. We are watching a recording in a sense. A 550-year-old recording played at the speed of light. The star we see might be a ghost, its light still travelling while the source has already been destroyed. There is a particular irony in the relationship between Antares and Betelgeuse that deserves careful attention. Both are red supergiants, both are supernova candidates, both are among the brightest stars in the night sky, both are visible to the naked eye, both have been studied extensively by modern astronomy, but Betelgeuse receives vastly more public attention, largely because of the dramatic dimming event of 2019 and 2020, which generated a frenzy of media coverage and social media speculation. Antares, by contrast, has been comparatively ignored by the popular press. It sits lower in the sky for Northern Hemisphere observers. It has not produced a headline-grabbing photometric event, and its name, while evocative, does not have the pop culture cachet of Betelgeuse, which benefits from its association with the movie of a similar name. This disparity is not justified by the science. Antares is a comparable or even superior target for supernova studies in several important ways. Its position in the southern sky gives it access to the world's best ground-based observatories, concentrated in the Atacama Desert of Chile. Its surface has been imaged in greater detail than Betelgeuse is, thanks to landmark observations with the Very Large Telescope Interferometer. Its extended atmosphere has been mapped with unprecedented resolution using ALMA, and its mass, while uncertain, may actually place it in a slightly more advanced evolutionary state than Betelgeuse, depending on which models and which mass estimates you trust. The preference for Betelgeuse in popular culture is understandable from a media standpoint. Betelgeuse is a brighter star in the sky. It is easily visible from the northern hemisphere, where most major media outlets are based. It is prominent in the familiar constellation of Orion, and its name is memorable and fun to pronounce. But from a scientific standpoint, Antares is at least equally important. The concentration of public attention on Betelgeuse has, paradoxically, left Antares somewhat understudied relative to its significance as a pre-supernova laboratory. It is the other red supergiant death candidate, and the word other in that phrase does not mean lesser. In some respects, Antares may be the more scientifically valuable of the two. Its distance, while uncertain, is reasonably well constrained and places it close enough for detailed study, but far enough for safety. Its companion star provides a reference point for measuring the circumstellar environment and for understanding the dynamics of the binary system before and after the explosion. Its position in the southern sky makes it accessible to some of the world's most powerful observing facilities, including the Very Large Telescope in Chile, the Atacama Large Millimeter Array, and the planned Extremely Large Telescope, and its relative stability, compared to the dramatic brightening and dimming episodes of Betelgeuse, makes it a more predictable target for long-term monitoring campaigns that require consistent baselines. Betelgeuse may be the more photogenic patient, but Antares may be the more informative one. There is also an argument from completeness. If we want to understand the final stages of massive stellar evolution, we need to study more than one example. Betelgeuse and Antares have different masses, different evolutionary histories, different mass loss rates, different circumstellar environments, and probably different core structures. By studying both, we can begin to disentangle the effects of mass, metallicity, rotation, and binarity on the pre-supernova evolution of red supergiants. By focusing on one and neglecting the other, we risk building a theory of stellar death that is calibrated to a single example and may not generalize. Science advances fastest when it has multiple data points, and in the field of nearby red supergiant studies, our sample is painfully small. We cannot afford to ignore half of it. Now let us consider the broader implications of what Antares represents in the cosmic cycle of matter. The elements that make up everything we know, the carbon in our cells, the oxygen we breathe, the iron in our blood, the calcium in our bones, the phosphorus in our DNA, were forged in stars like Antares. Not in Antares itself, necessarily, since Antares has not yet exploded, but in stars of similar mass and evolutionary history that exploded billions of years ago, seeding the interstellar medium with heavy elements that eventually coalesced into new stars, new planets, and eventually life. The solar system formed from a cloud of gas that was enriched by the debris of multiple previous supernovae. We are, quite literally, built from the wreckage of dead stars. When Antares explodes, it will perform this same act of cosmic generosity one more time. Its supernova will scatter newly forged elements into space, elements that were created in the final seconds of core collapse, including many of the heaviest elements on the periodic table. Elements heavier than iron, such as gold, platinum, uranium, and many others, are primarily produced through rapid neutron capture processes that occur during the explosion itself in the intense neutron flux of the expanding supernova ejector. These elements will mix with the surrounding interstellar gas, enriching it, and in millions of years they will be incorporated into new star-forming regions, new molecular clouds, new protoplanetary disks, new planets, and potentially new forms of life. This is the deeper truth, the truth that transforms the death of Antares from a story of destruction into a story of continuity. Death and creation are not opposites in the cosmos. They are the same process, viewed from different scales and different moments in time. The death of a star is the birth of a nebula. The collapse of a core is the creation of a neutron star. The explosion that destroys a solar system seeds the raw materials for new ones. Antares will die, but its material will live on, recycled endlessly through the galaxy, participating in cycles of formation and destruction that have been running for nearly 14 billion years and will continue for trillions more. The atoms that are currently inside Antares will one day be inside other things, other stars, other planets, perhaps other living things in places and times so distant from our own that we cannot begin to imagine them. This is not comfort in the human sense. The death of Antares will be violent, indifferent, and total. No consciousness will survive it. No memory of the star's existence will be encoded in its remnants. The neutron star or black hole left behind will carry no record of the red supergiant it once was. The expanding shell of debris will carry no memory of the mythologies that were built around its light. Everything that Antares meant to us, the rival of Mars, the heart of the Scorpion, the navigation point, the seasonal marker, the source of wonder and fear, will exist only in human records and human memory. The star itself will be gone. And yet there is something magnificent about this cycle, something that transcends the coldness of the physics. The fact that we can stand on this small rocky planet, orbiting an unremarkable star in the outer suburbs of an ordinary spiral galaxy, look up at a red point of light 550 light-years away, and understand in precise quantitative detail the processes that will destroy it, that we can predict its death, calculate the brightness of its explosion, estimate the energy of its neutrino burst, model the formation of its remnant, identify the elements it will create. This capacity for understanding is, as far as we know, the most extraordinary thing in the entire observable universe. Matter has organized itself, briefly and improbably, into forms that can comprehend their own origins, their own composition, and their own destruction. We are the cosmos looking back at itself with understanding, and Antares is one of the objects we have chosen to understand. There is a concept in philosophy called the overview effect, first described by Frank White in 1987. It refers to the cognitive shift experienced by astronauts who see the Earth from space for the first time. The planet appears small, fragile, and singular, a blue marble suspended in the void, with no visible borders, no visible conflicts, just a thin atmosphere separating life from the vacuum of space. Astronauts who have experienced this shift report a profound change in perspective, a sense of the preciousness and fragility of the world that does not fade even after they return to the ground. Antares offers something analogous, but in reverse. Call it the depth effect. Instead of looking outward from orbit and seeing our world from above, we look outward from the ground and see a star that dwarfs our world beyond comprehension. A star whose diameter exceeds the orbit of Mars. A star whose surface area is millions of times greater than Earth's. A star that is pouring out energy at a rate that makes our sun look like a candle. And this star, this incomprehensibly vast furnace of nuclear fire, is dying. It is temporary. It will not last. If something that large and that powerful and that ancient is temporary, then what does permanence even mean? The depth effect does not make our world seem less important. If anything, it makes it seem more remarkable. In the midst of all this cosmic violence and indifference, on a small rocky planet orbiting a small yellow star, matter organized itself into living things. Living things that can look up at Antares and understand what they are seeing. Living things that can calculate the neutrino flux from a star 550 light-years away and predict, with quantitative precision, the brightness of its eventual explosion. The universe is not hostile to life. It is indifferent, and within that indifference, life has carved out a niche of awareness and understanding that is, as far as we know, unique. Antares does not know it is dying. We do. And that knowledge, that awareness of cosmic mortality, is perhaps the most precious thing that matter has ever produced. What does it mean for humanity that one of the brightest, most recognizable stars in the sky is going to die? On a purely practical level, very little. Earth will not be harmed by the explosion. The ozone layer will remain intact. The radiation flux at our distance will be well below any biologically significant threshold. Life will continue. Crops will grow. The tides will rise and fall. The seasons will turn. We are safe, in every physical sense of the word. But safety is not the same as indifference. And the death of Antares, whenever it comes, will carry implications that go far beyond the physics of radiation transport and atmospheric chemistry. Consider for a moment the cultural weight of a constellation losing its brightest star. Scorpius has been recognized as a coherent star pattern for at least 5,000 years. It is one of the oldest known asterisms, identified independently by civilizations on every inhabited continent. The Sumerians knew it. The Egyptians knew it. The Greeks knew it. Indigenous Australians knew it. The Maya knew it. Polynesian navigators used it to cross the Pacific. For all of these cultures, the red star at the Scorpion's heart was a landmark, a calendar marker, a mythological anchor, a navigational tool. The loss of that star, its replacement by a temporary blaze of supernova light, followed by an empty spot in the pattern, would be immediately and universally noticeable. Every culture that looks at the southern sky would see the change. The Scorpion would be incomplete, diminished, missing its most vital point. For astronomers, the supernova would be both a loss and an extraordinary scientific windfall. A loss, because one of the most studied and most scientifically valuable nearby red supergiants would be gone, replaced by a rapidly evolving supernova remnant that, while fascinating in its own right, would no longer serve as a laboratory for pre-supernova stellar physics. An opportunity because the explosion itself would generate more data about supernova mechanisms than all previous observations in the history of astronomy combined. The neutrino detectors would record not dozens or hundreds, but potentially millions of individual neutrino interactions. Each one would carry information about the temperature, density, and composition of the collapsing core. The total number of detected neutrinos, their energy spectrum, their arrival times, and their flavor ratios would constrain the nuclear equation of state, the relationship between pressure and density at extreme conditions that determines the maximum mass of a neutron star and the behavior of matter at supranuclear densities. This is physics that cannot be tested in any laboratory on Earth. It can only be tested in the core of a collapsing star. The gravitational wave observatories, LIGO, Virgo, CAGRA, and any future detectors operating at that time would search for the gravitational wave signal of core collapse and neutron star formation. This signal has been predicted theoretically, but has never been detected. It would provide information about the asymmetry of the collapse, the rotation rate of the neutron star, and the dynamics of the explosion mechanism that electromagnetic observations alone cannot provide. A detection, or even a meaningful upper limit, would be a milestone in gravitational wave astronomy. The combination of neutrino data, gravitational wave data, and electromagnetic observations across the spectrum would provide what physicists call multi-messenger astronomy at its most powerful. Each messenger, photons, neutrinos, and gravitational waves, carries different information about the explosion, information that is complementary rather than redundant. The photons tell us about the surface and the expanding ejecta. The neutrinos tell us about the collapsing core and the formation of the compact remnant. The gravitational waves tell us about the bulk motion of matter during the collapse and the asymmetries in the explosion. Together, they would paint a three-dimensional, time-resolved portrait of a core collapse supernova that would be orders of magnitude more detailed than anything we have ever obtained. The scientific papers that would result from such an event would fill entire journal volumes. The datasets would be analyzed for decades. Theoretical models that have been debated for years would be confirmed, refined, or discarded overnight. It would be, in every meaningful sense, the Rosetta Stone of stellar astrophysics. The electromagnetic observations across the entire spectrum would track the supernova from its first appearance through peak brightness and into its long decline. Each wavelength band would tell a different part of the story. Radio observations would reveal the interaction of the blast wave with the circumstellar medium. Infrared observations would track the formation and cooling of dust in the expanding ejecta. Optical observations would measure the light curve and spectral evolution. Ultraviolet and X-ray observations would probe the hottest, most energetic regions of the expanding shell. Gamma-ray observations would search for signatures of radioactive decay and high-energy particle acceleration. The data would settle debates that have persisted for decades. Is the neutrino-driven mechanism truly responsible for reviving the stalled shock wave, or do magneto-hydrodynamic effects play a crucial role? What fraction of the iron group elements produced in the explosion is nickel-56 versus other isotopes? How much mass is ejected, and at what velocities? What is the morphology of the explosion? Is it spherically symmetric, jet-driven, or something in between? How does the supernova remnant evolve in its earliest stages? Each of these questions has been the subject of hundreds of theoretical papers and vigorous scientific debate. A single nearby supernova would provide definitive answers to most of them. But beyond the science, beyond the data, and the papers and the Nobel Prizes that would surely follow, there is a human dimension that resists quantification. We live in an age of unprecedented astronomical knowledge. We have mapped the cosmic microwave background, the afterglow of the Big Bang. We have detected gravitational waves from merging black holes. We have imaged the shadow of a supermassive black hole in the galaxy Messier 87. We have launched telescopes beyond Earth's atmosphere that can see galaxies as they were billions of years ago. We know more about the universe than any previous generation could have imagined. And yet, for all this knowledge, we remain fundamentally small. We are creatures of a single planet, orbiting a single star, in a galaxy of hundreds of billions of stars, in a universe of hundreds of billions of galaxies. We cannot prevent Antares from exploding. We cannot deflect its light. We cannot protect the constellation. We cannot rearrange the stars. We can only watch and understand and record what we see. This is our role. This is what our intelligence allows us to do. Not to control the cosmos, but to comprehend it. Not to change the outcome, but to witness it with awareness. There is a particular quality of awareness that comes from knowing something is doomed, but not knowing when the end will arrive. It is an awareness that sharpens attention, that makes each observation feel more precious, each measurement more urgent. Every time an astronomer points a telescope at Antares and records its spectrum, its brightness, its pulsation state, they are doing two things simultaneously. They are adding to our understanding of the star, and they are confirming that it is still there, still burning, still alive. Every observation of Antares is a wellness check on a dying patient whose timeline is unknown. There is also a temporal dimension to this reflection that deserves attention. Human beings tend to think of the present moment as special, as a unique and privileged point in the timeline of the universe. Psychologists call this the present bias, the tendency to overweight current experience relative to past or future experience. But in the context of Antares, the present moment is genuinely special, though not in the way we usually think. We are living in the brief window of cosmic time, during which Antares exists as a visible red supergiant. This window began roughly 1 to 2 million years ago, and will end at some point in the next 100,000 years, possibly much sooner. Before this window, Antares was a hot blue main sequence star, far less visually impressive, but far more stable. After this window, Antares will be a supernova remnant and a compact object, a neutron star or black hole, invisible to the naked eye and detectable only with sophisticated instruments. The total duration of the red supergiant window is perhaps 2 million years out of a total stellar lifetime of 12 million years. That is roughly 17% of the star's life. And the total duration of human civilization is roughly 5,000 years out of those 2 million, which is 1/4 of 1%. We happen to exist during the brief period when Antares looks the way it does, red and immense and luminous, and why happen to have developed the technology to understand what we are seeing. This is not a coincidence that demands explanation. It is simply a fact, but it is a fact worth noting, because it reminds us that the sky we see tonight is not the sky that always was or always will be. It is the sky of this moment, this epoch, this fleeting intersection of our existence with the existence of the stars. Perhaps the healthiest response to this situation is the simplest one. Look up, see the star, know what it is, know what it will become, know that its death is certain and its timing is unknown, and then continue with the business of living, carrying with you the awareness that the universe is not static, not permanent, not designed for our comfort. The night sky is temporary. The constellations are temporary. We are temporary. And this shared impermanence, this common mortality of stars and civilizations and individual human lives, is not a cause for despair. It is a cause for paying attention, for being present, for seeing what is here now before it changes. Antares has been telling its story for millions of years. The red light we see tonight was emitted by a star already well into its death throes. A star whose core is a furnace of progressively heavier elements, whose outer layers are being flung into space by turbulent convective motions, whose companion star orbits patiently at a distance of 550 astronomical units, waiting for the end that will rewrite its own trajectory through the galaxy. Every photon that reaches our eyes from Antares carries information about these processes. Every observation adds another sentence to the story, and the story is nearing its end. Not tonight, probably. Not this year, almost certainly. Not this millennium, most likely. But soon. Soon by the standards of a universe that measures time in billions of years. Soon by the standards of a galaxy that has seen billions of stars born and die. Antares will reach its final chapter. The core will turn to iron. The fusion will cease. The collapse will begin. And for a few brilliant weeks, the heart of the Scorpion will outshine everything else in the night sky, blazing with a light that announces both its death and its transformation. We will be here to see it, or our descendants will, and they will remember, as we remember now, that the stars are not eternal, that the sky is not fixed, that the universe is a place of constant change, constant creation, constant destruction, and that the beauty of it lies not in its permanence, but in its impermanence, in the fact that things change, that stars die, that new ones are born from the debris, and that somewhere, on some small planet, orbiting some quiet star, made from the recycled remnants of ancient supernovae, a species evolved that was clever enough to figure all of this out. And so we return to where we began. There is a star in the southern sky. It is red, it is enormous, it is dying. Its name means the rival of a god, and for thousands of years it has held that name with quiet dignity, pulsing with a light that has travelled 550 years to reach our eyes. 550 years of silence. 550 years of crossing the void between that immense aging furnace and this small, fragile world. Antares does not know it is dying. It has no awareness, no intention, no narrative. It is a sphere of gas and plasma, governed by the laws of physics, following a path that was determined the moment it first ignited its nuclear furnace millions of years ago. Every stage of its life was written in its initial mass and composition. Every phase of its evolution was inevitable from the first instant of hydrogen fusion. The red supergiant we see tonight is not a choice, it is a consequence. The consequence of gravity and pressure and nuclear physics operating on a specific quantity of matter for a specific span of time. Nothing more, nothing less. And yet, we cannot help but see it as something more. We named it, we placed it at the heart of a scorpion. We called it the rival of Mars and tracked its movements across the sky for thousands of years. We used it to navigate oceans, mark the turning of seasons, tell stories about gods and monsters and the shapes we see in the dark. We gave it meaning that it does not possess and cannot comprehend, and in doing so, we revealed something fundamental about ourselves. We are meaning-making creatures. We look at a cloud of gas 550 light-years away, a cloud that is slowly, inevitably, inexorably falling apart, and we see a heart, a rival, a portent, a mystery. The star does not care. The star cannot care. But we do. And that caring is not a weakness. It is, perhaps, the most remarkable thing in this story. When Antares finally dies, whatever century or millennium that occurs, it will not be a personal loss in the way that human deaths are personal. No consciousness will end. No voice will fall silent. No hand will go still. But something will be lost nonetheless. A familiar light will vanish from the sky. A pattern that has been stable for the entire history of human civilization. A pattern that Sumerian priests and Egyptian architects and Greek philosophers and Polynesian navigators and modern astronomers have all looked upon and recognized. That pattern will change. And every human who has ever looked up at Scorpius and seen that red point glowing at its center, across all the centuries and all the continents, and all the languages and all the belief systems, will be connected, across time, by the shared experience of having seen something that is now gone. That connection across time is one of the quiet gifts of the night sky. It links us to our ancestors, and through the stars that still remain, to our descendants. We are temporary patterns in matter and energy, briefly complex enough to understand our own impermanence. Antares is a temporary pattern too, on a vastly larger scale, but governed by the same physics. The difference is that we know we are temporary. Antares does not, and there is something both humbling and ennobling about that difference. We are small, fragile, short-lived creatures on a small, fragile planet, orbiting an unremarkable star in the outer reaches of an ordinary galaxy, and we have figured out how stars die. We have peered into the core of a red supergiant with our instruments and our mathematics and our relentless curiosity, and we have seen the iron that will end it. We have calculated the neutrino burst. We have modelled the shock wave. We have predicted the light curve. We have identified the remnant. We have understood the physics of an event so energetic that it will briefly outshine an entire galaxy. All of this, from our little world, with our little brains, in our little span of years. We cannot stop it. We cannot change it. We cannot negotiate with gravity. We cannot replenish the fuel. We can only understand it. And perhaps that is enough. Perhaps understanding is the highest form of participation that the universe allows to creatures like us. We cannot shape the cosmos, but we can comprehend it. We cannot extend the life of a star, but we can know, with precision and depth and honesty, exactly how and why it will end. That knowledge does not change the outcome, but it changes us. It changes what it means to look up at the sky and see a red point of light and know what it is. Not just a light, not just a star, a dying furnace of nuclear fire, billions of times more massive than anything on Earth, older than civilization, brighter than imagination, and doomed. The night sky will continue to turn. The constellations will continue their slow drift, shifting over millennia as the stars move along their separate paths through the galaxy. Scorpius will endure for a while longer, its curved tail sweeping across the southern horizon, its claws reaching toward the scales of Libra, its heart glowing red with the light of a star that is running out of time. Generations will come and go, telescopes will improve, theories will be refined, new instruments will be built, new detectors, new observatories, new ways of listening to the universe. And through all of it, Antares will sit there, red and vast and slowly dying, waiting for the moment that only the laws of physics can determine. And then, one day, the heart will stop. A flash of light, brighter than anything the modern world has ever seen. A brilliance that turns night into day and casts sharp shadows on the ground and forces every eye on Earth to look up and see the end of something ancient. And then, slowly, a fading, a dimming, a gradual return to the darkness from which the star first emerged 12 million years ago. When the first hydrogen atoms, like a collapsing cloud, reached the temperatures and pressures needed to fuse, the remnant will glow for centuries, a wispy shell of expanding gas, lit from within by the radioactive decay of the elements forged in the explosion. Astronomers of future centuries will study it with instruments we cannot imagine, extracting secrets we cannot yet formulate as questions. Then that too will fade, dispersing into the interstellar medium, becoming part of the raw material for the next generation of stars and planets. The neutron star at the center will cool, slowly, over billions of years, radiating away the heat of its violent birth into the cold of intergalactic space. Or, if the remnant is massive enough, a black hole will sit in the silence, invisible except for its gravitational influence, bending spacetime around a point of infinite density, a monument to the star that once rivaled a god. This is the cycle: birth, fusion, expansion, collapse, explosion, dispersal, rebirth. It has been running for nearly 14 billion years, since the first generation of stars ignited in the dark aftermath of the Big Bang and began the long process of enriching the universe with heavy elements. It will continue for trillions of years to come, long after the last red dwarfs have exhausted their hydrogen and the last white dwarfs have cooled to black, long after the galaxies have drifted apart and the cosmic background radiation has faded to nothing. Antares is one iteration of this cycle, one star among 400 billion in this galaxy alone, one death among the billions that have already occurred and the billions yet to come. But it is the one we can see, it is the one we have named, it is the one we have studied and measured and modelled and worried about. It is the one whose death we are waiting for, with instruments trained on its light, with theories constructed around its physics, with a strange, quiet, very human awareness that somewhere inside that red point of light, in a core we cannot see and a process we cannot stop, a clock is ticking. Look up tonight. If the sky is clear and Scorpius hangs above the southern horizon, find the red star at the Scorpion's heart. It is there. It has been there for every generation of every civilization that has ever existed on this planet. It was there when the first cities were built along the Tigris and the Euphrates. It was there when the pyramids rose from the desert sand. It was there when Rome fell, and when Constantinople fell, and when the first ships crossed the Atlantic. It was there when the first telescope was pointed at the sky, and when the first rocket left the atmosphere. It is still there now, tonight, 550 light-years away, red and ancient and slowly, silently, inevitably dying. For now, the cosmos does not owe us permanence. It does not owe us stability. It does not owe us a night sky that looks the same from century to century or from millennium to millennium. What it gives us, what it has always given us, is this moment, this brief window of time in which we can look up and see and wonder and understand. Antares is a gift from the universe to itself, a furnace of creation and destruction that has been running for millions of years and will end in a single, catastrophic instant that will briefly outshine billions of suns. And we, the temporary patterns, the self-aware arrangements of carbon and oxygen and iron, we are here to witness it, to know what it is, to understand why it will end, to feel something when we look at it, even if the star itself feels nothing at all. That is enough. That has to be enough, because it is all we have. Somewhere in the constellation Scorpius, the heart is still beating. Red light still pours from its surface, crossing the void at 300,000 kilometers per second, carrying news of a star that may already be dead. The light does not know. The light does not care. It simply travels as it has always traveled, as it will always travel, long after the source that created it has been torn apart by forces that no will or wish or prayer can oppose. The heart is still beating, but it will not beat forever, and when it stops, the silence that follows will be the deepest silence the sky has ever known.